Hello students, in this video we are going to discuss defects of human eye. So the first defect that we are going to discuss is myopia. Now what is myopia? Myopia is also known as nearsightedness. What does that mean? That simply means that a person cannot see far object, or you can say the person has a limited vision. He cannot see a very far object from his position. This type of defect leads to a person's far point getting less than infinity. A person with this defect has the far point near than infinity. This point is very important. What this state? This state that the person's visibility has got reduced and he cannot now see infinite objects at infinite distances. Such a person may see clearly up to a distance of few meters. Now he can only see objects kept at a distance of few meters. Okay. The next point that is important is the image of a distance object is formed in front of retina. The image has to form on the retina, but in the case of myopia, the image of a distance object is formed in front of retina. Now this is again the problem that a myopic eye suffers. Where the image has to be produced, the image has to be produced at the retina itself. Okay, but the image is getting produced in front of the retina. Now there are two reasons because of which this defect arises. The first reason is excessive curvature of eye lens, and the second reason is elongation of eyeball. So the two reasons because of which a myopic vision is possible is that excessive curvature of eye lens, and second is elongation of eyeball. This defect can be corrected by using a concave lens. Now, what type of lens we have to recommend a person with myopic eyes? Concave lens. Again, this point is important. This is illustrated in figure 10.2. Now we can see this figure. In this figure, you can see the far point of a myopic eye. This is the far point of the myopic eye here. The O that is shown over here is the far point. Now, if this is the far point, then we can also call this distance to be object distance. If the person has to see an object at infinity, if the object is kept at infinity, then image is formed in front of the retina and not at the retina. This is the place where retina is, and here the image has to be formed, but the image is forming over here in front of retina. To correct this type of defect, what we have to do? We have to place a concave lens. When a concave lens is provided, now we can observe that if the object is placed at an object distance O, then we can easily see the object. When the object is placed at infinity, in that case, the image will be produced on the point O. So, when u equals to infinity, in that case, the image has to be produced at the far point of myopic eye. Far point of myopic eye. And by this way, we can calculate the focus of correction lens. While considering this, we also have to be clear that V will be considered negative. And when V will be considered negative, obviously the focal length of correction lens will also be negative. Okay, so this is all we have to remember while solving the numerical. When you will be solving a numerical on based of myopic vision, defect of myopic vision, you have to remember that the object distance is considered to be infinity, the image distance is to be the far point of myopic eye, and focus or focal length is the distance that if the focal length is the focus of correction lens that we use. Okay, so let us now take an example of myopic defect of myopic vision. This will be a numerical, and in the numerical we will understand how we can solve a numerical based on myopic vision. Let us take, for example, question 6. What is given in this question? The far point of myopic person is 80 centimeter in front of the eye. What is the nature and power of lens required to correct the problem? So what is asked? We are questioned to give what is the power of lens, and we also have to describe type of lens that is to be used for correction. So what we are given is we have the image distance that is 80 centimeter. Now how we got to know this is the image distance? See, the person can only see up to 80 centimeter. When he can only see up to 80 centimeter, that simply means that the image that we have to produce of object at infinite distance has to be at a distance of 80 centimeter at maximum. If the image of an infinite object is produced at 81 centimeter, the person will not be able to see because he can see only up to 80 centimeter. Okay, so what we have? We have the object distance, and that is 80 centimeter. Now again, we will have to consider it to be negative because this will be in front of the lens, and by the sign convention we have to consider it to be negative. Now by use of lens formula, we have 1 by v minus 1 by u equals to 1 by f. Okay, so this is the formula that we are going to use, and this formula is called as lens formula. So what we are going to do with this formula? we will be putting 1 by minus 80. Now I have to subtract 1 by u. Now what we are going to consider the u. U is object distance, and we want this myopic person to be able to view infinite distance. So in this case, we will consider the object distance u to be equal to infinity. So 1 by infinity is equals to 1 by f. Now if we divide 1 by infinity, it will give us 0. So in this case, we will be getting f equals to minus 80 centimeters. We have simply calculated what we have calculated. We have simply calculated the focal length. Now, if you know the formula for calculating power of lens, what you are going to do? You simply have to do 1 by f, where f is to be measured in meters. Now, in this case, we have the power that is to be calculated for a focal length of 80 centimeter. So when it is in centimeter, we will have to write 80 over here and 100 over the numerator. That is how only we can convert focus that is in meter into centimeter. Now we also have to use the sign, that is minus 80. So what we get? We get by dividing, we get 5 by 4, minus 5 by 4, which is equals to minus 1 point. When we divide 5 by 4, we get 1.25, and this is the power, minus 1.25 diopter. Here minus sign indicates what type of lens we have to use. We have to use concave lens, because a concave lens has negative power. Okay, so we know the type of lens, we also know the power of lens, and that is all about the numerical based on myopic vision. So now when we have solved a numerical on defect of myopic vision, we can easily conclude now that a concave lens of suitable power is required for the correction of myopic vision. So to take a recap of the topic that we have discussed right now, we can say that a myopic vision is also called as nearsightedness. So it is an important point. Again, a person with myopic vision means that the person is having a defect, and because of this defect, he can only see objects that are near to him, and he cannot see the object at infinity. Third point that is of importance is that the image is not getting formed on the retina, it is getting formed in front of the retina. So we have to remember that where the image is getting formed. The next point is that the defect may arise due to two conditions, that is excessive curvature of the eye lens, and second, elongation of eyeball. And lastly, for correction, what we require? We require concave lens of suitable power. That's all about myopic vision. Now we will be discussing hypermetropia. Hypermetropia is the opposite case of myopia. Why it is called the opposite case of myopia? Because in this case, the person is capable of having a vision of far objects, but he is not capable of observing objects at its near point. That is, uh, a person suffering from hypermetropia cannot see object at near point. He can only observe objects that are far away from it. This means the near point for the person is farther away from the normal near point, that is 25 centimeters. Okay, such a person has to keep a reading material much beyond 25 centimeter. If he has to read something, he will have to keep it away from it, much away from 25 centimeter. Then in this case, we can say that the person is suffering from hypermetropia. Why this is happening? This is because the light rays from a close by object are focused at a point behind the retina, but the image has to be formed on the retina. So we can say that the image that is getting formed in hypermetropia is beyond the retina or behind the retina. Again, there are two reasons because of which this defect arises. This defect arises because of the focal length of the eye lens is too long, and the second is the eyeball has become too small. So hypermetropia is the condition when the eyeball becomes too small, and another possibility is that the focal length of eye lens is too long. Now what we can do to correct this type of defect, we can use a convex lens of appropriate power, and this is illustrated in figure 10.3. Let us see what the figure suggests us. So see, let's if we have to look at the figure A, near point of hypermetropic eyes, then you can simply observe that the person is now not capable of observing the object at a normal near point, that is 25 centimeter. He is capable of observing object at a new normal that is more than 25 centimeter. Okay. Now, if we have to make his eye justified, we need to produce this image, the image of the normal near point to the point where he can now actually see the image getting produced, that is n, that is this point. Let us see what this defect leads to. The figure B over here shows what the defect is actually. When the person tries to observe an object at a normal near point, the normal near point is 25 centimeter. So when the person want to observe an object that is kept at 25 centimeter, then the image is produced behind the retina. This is the place where image is produced, right? Image is produced behind retina, but the image had to be produced at the retina. Here the image had to be produced. Now let's see the correction of hypermetropic eyes. For the correction of hypermetropic eye, what we have to do? We have to produce the image of an object that is placed at n prime to n. and this is possible only by the use of a convex lens. So the correction lens is a convex lens, and by the use of this convex lens we are going to produce an image of the object placed at near point to a far point which is visible to this hypermetropic eye. So that is all about the theory and the diagram. Now we will be discussing a numerical on this topic, that is hypermetropia. Okay. For an example of a numerical based on hypermetropic vision, let us take question number 7. What this question is about: make a diagram to show how hypermetropia is corrected. In response to this question, you will have to draw the diagram of the third section that we just discussed. In that diagram, you will also have to show the convex lens that is used for correction of a hypermetropic vision. Okay. So in the next part of the question, what we have to do, the near point of a hypermetropic eye is 1 meter. It is given that the near point is 1 meter. For what type of eye? Hypermetropic eye. Matlab, the person is suffering from hypermetropic defect. What is the power of lens required to correct this defect? Now the question is, what is the power of the lens that is required to correct this defect? We will be calculating power of the lens. Okay. When we have to calculate the power of the lens, we obviously have to calculate the focal length. Focal length need to be calculated when we have to calculate the power of the lens, because we know that the formula of power is 1 by f, where f is in meter, and the unit for power in this case will be diopter. Okay. So this is what we have to do. It is also mentioned over here that we have to assume near point of normal eye is 25 centimeter. Okay. So we have all the necessary numeric values that is required for solving this question. Now let us erase these things so that we have the space to solve our question. Considering the values that are given in the question, we can now easily state that the object which we want to see is kept at a distance of 25 centimeter on the left hand side of the lens, and the image of this object is to be produced at 1 meter. Okay. Now when we have to calculate the focal length of the lens which can produce image at 1 meter of distance when object is placed at 25 centimeter, then what we can do, we simply have to go to the lens formula, and the lens formula is 1 by v minus 1 by u is equals to 1 by f. So using this lens formula, we are going to calculate the focal length. So for this, what we are going to do now, we will simply place the values, numeric values in the formula, and we will get now if we correct the sign, we will get that 1 by 25 minus 1. This is equal to Now what we have to do, we have this value that is to be calculated, but we have missed something. What we have missed? We have missed the units. You can see the object distance is in centimeter, whereas the image distance is in meter. So to overcome this, we have to convert all of them into meter. So let us convert this into meter. To convert this into meter, we will have to put 100 in the numerator of 1 by v. So now we have 4 minus 1, that is 3, and the value is plus 3. Obviously what we have found over here is 1 by f, and we know that 1 by f is equals to power when calculated in meters. So the value of power of lens will be plus 3 diopter. And here the plus sign indicates the lens that we have used is a convex lens. Okay, so this is all about the numerical based on hypermetropic defect of vision. As we have now observed the numerical, we can easily understand that the object that we want to see is kept at normal near point, and its image is produced at the near point of a hypermetropic eye. This image is now visualized by the eye lens, and the image of this image will be produced on the retina, and that is how the person will be able to observe an object at normal near point when he is suffering from hypermetropia. Okay, so the conclusion based on the numerical and the theory is that we require a convex lens for correction of hypermetropic vision. Second point is that the defect arises due to focal length of eye lens getting too long, or the eyeball has become too small. So these are the two factors leading to these defects. We also have to remember in some case that normal near point is 25 centimeter. So the normal near point is 25 centimeter. And that is all about hypermetropia. Now let us talk about presbyopia. So what is presbyopia? The power of accommodation of eye usually decreases with aging. When we age, the power of accommodation of the eye decreases, and this lead to problem of adjusting our eye lens and observing object at both near and far points. So most people suffer this problem, and they are not able to observe near object as well as object which are kept at far distance. This defect is called presbyopia. It arises due to gradual weakening of ciliary muscles. When ciliary muscles get weakened, when ciliary muscles are weak, then this problem arises. And this is also because of diminished flexibility of the eye lens. So again, there are two reasons because of which presbyopia can happen. This is the condition where the person is suffering from both myopia and hypermetropia. So what he will be requiring? He will require a bifocal lens. A bifocal lens is a combination of two type of lenses. Both concave and convex lens are used in bifocal lenses. So these type of lens are observed in spectacles of old people, old age people, where in their spectacle two parts are defined. One to observe far point, and the other part of the lens is used for observing near near objects, like for reading. And for observing far object, they have the upper part of the lens. These objects which are at far distance require concave lens, and to read objects at near distance we require convex lens. So the correction of a presbyopic eye is by bifocal lens, and a bifocal lens consists of both concave and convex lenses. Here you can see the upper portion consists of a concave lens because we have to see far objects, and the lower part is convex lens. So that is all about defects of human eye. Thank you.